So anyway, optimization goals. For our first goal, kind of these optimizations, is that we would like our apps to launch quickly. When a user taps on an app, we want to be able to interact with that app as soon as possible, and this is called startup time. Before a function can execute, it needs to be in memory, and if it's not, the kernel will load it into memory for you. This is called a page fault, and it slows down execution. So fewer page faults generally means a faster startup time in the mobile space. And it also turns out that a smaller text size or a smaller binary generally yields fewer page faults, which in turn gives you a faster startup time. So for this reason, we tend to build our apps with OZ optimization, which optimizes for size instead of for speed. It may sound counterintuitive, but in the mobile space, O2 optimization makes apps start up slower than OZ optimization, mostly because inlining tends to increase code size. For our second optimization goal, we'd like our apps to be as small as possible. When a user installs an app, they are downloading an IPA file, which is basically a zip file of the contents of the app. And we like to minimize the IPA size so that users can install and update our apps fast. And on many of the apps that we've seen, executables make about 80% of the whole app size, the other 20% being images and other assets. So this kind of shows that the compiler really does have a lot of control over the overall size of the app. So can we use profile-guided optimization to improve startup time for our mobile apps? In LLVM, we have IRPGO, which is enabled with the fprofile generate and the fprofile use flags. Unfortunately, by default, this PGO can drastically increase the size of the binary because it tends to be used to guide inlining decisions, which increases the size of our binaries. Some of this overhead can be mitigated with the disable pre-inline flag or the PGSO flag, which stands for Profile Guided Size Optimization. As a side note, I just wanted to put these flags on my slide in case it saves anyone debugging time, because it took me a while to track down these flags. So anyway, the default PGO becomes not very useful in the mobile space because it does increase code size. So we've extended IRPGO with temporal profiling with the goal of improving startup performance by generating an order file we can use. Temporal profiling is enabled with the PGO temporal instrumentation flag. And this tells IRPGO to collect function timestamps at instrumentation time. And this measures when each function was called for the first time. It basically it profiles the temporal behavior of our functions. Temporal profiling has been upstreamed in LLVM, so you're free to check out the details. And I also wanted to mention that a while back, I gave a talk on lightweight instrumentation, which removes the code size bloat from instrumented binaries. And temporal profiling is fully compatible with this. So let's take a look at the details of temporal profiling. For each function we want to instrument, we create a new timestamp variable that is initialized to 0. When a function is called for the first time, we set that timestamp to the value of the global timestamp, and then we increment that global timestamp. When the raw profile is dumped, we get a timestamp value for each function. In this example, and then we can sort our functions by timestamps to get a function trace. So in this example, we have, in our first trace, we have foo, goo, and bar in our from our first raw profile. In our second trace, we only have foo and bar. And the function goo is not in the trace because it was not executed. And we know that because the timestamp of goo is 0. And finally, we can merge these raw profiles and their traces into an index profile using the LLVM prof data tool. And you might be wondering if we can use just a single one of these traces as an order file to improve startup time by reducing page faults. And the problem is this would optimize for a single startup path out of, and you might have potentially like many of these raw profiles you generate. So how would you select just one trace to use as an order file? What we want is to merge many traces from many different startups to generate an order file that is representative of startup paths that we see in production. The question is, how do we actually merge these traces to generate an order file? And before I answer that question, let's talk about compressed size for a minute. Compressed size depends on the number of distinct sequences in a 64 kilobyte sliding window. I know this is a lot of words, but think of a sequence as an instruction. And this becomes, if you have a lot of similar instructions in a small window, you can actually improve compression. So if you co-locate functions that have similar instructions close together in a binary, you'll be able to end up with a smaller compressed size. So in this example, we have some functions and they have textures that kind of show, hopefully you can see, show the contents of these functions. So with this arbitrary function order, we're going to get a poor compression. The compressed size will be larger in the end. But then if we reorder these functions so that functions with similar textures are close together, or functions with similar instructions are close together, then we will reduce the compressed size in the end. So we've developed an algorithm called Balanced Partitioning that can order functions to minimize some objective. We can use function traces from our indexed profile to improve startup time by minimizing the number of page faults during startup. And we can use the contents of our functions, or just the instructions of our functions, to improve the compressed size. Most likely, you'll want to minimize page faults for, you most likely want to minimize page faults for hot functions, or functions that are used during startup. And you want to reduce the compressed size for your cold functions that might not be used as much. Balanced partitioning is a fast algorithm. And this, I just wanted to give it a quick example. I was able to order 1 million functions in about 20 seconds, which is plenty fast enough in the context of build time. And balanced partitioning has been upstreamed to LLVM, so you are free to check out the details. So let's take a look at some of the details of balanced partitioning. Here we have a couple of functions, each with some instructions. And for each instruction, we can compute a stable hash. Then we can create a graph where we have function nodes, F1 through F4 on the bottom. And then we have utility vertices at the top, where you have a single utility vertex for each unique stable hash that you have. Then you can draw an edge from your functions to your utility vertices if that function contains that stable hash. So in this example, function F1 has 2 instructions that are turned into 2 stable hashes, U1 and U2. And we have edges from F1 and U1 and U2. And we can draw the rest of these edges in our graph. And at the end of the day, we'd like to reorder these functions so that functions end up close together if they share edges with similar utility vertices. Balanced partitioning is a recursive algorithm, so we start off with a group of unordered functions. Then we partition our functions into 2 groups, 2 roughly equal groups. And we do this recursively, so for each of our groups, we partition them further until eventually our groups are small enough that we can simply lay out the functions in the order that we have found. And the question is, how do we actually bisect these functions? How do we decide if a function should go into the left bucket or the right bucket? So I'll kind of try to show this. And here we have this graph that I constructed earlier, where we have functions in blue on the bottom and then utility vertices on top. And we have this initial partition where some of the functions are in the left bucket and some are in the right bucket. And if we take a look at just a single one of these utility vertices, this one in orange, it has edges only for functions in the left bucket. And we consider this good because these functions share the same utility vertex, and they're in the same group, so they are co-located close together. On the other hand, if you have this utility vertex in purple, it has edges that span the two buckets. It has edges in both the left and right buckets. And we consider this bad because functions are sharing this utility vertex, but they are far apart from each other. So they will end up far apart in the final binary. And we can create a cost function that essentially counts the number of edges that spans the two buckets. And by minimizing this cost function, we want to minimize this cost function. And we do this by swapping functions between buckets if it improves the cost function. So this kind of shows you at a high level how the balanced partitioning algorithm works. I've shown you how we can improve compressed size because I've defined the utility vertex based on the stable hashes that come from the instructions from the function. But we can also define the utility vertex based on the function traces that we have in our index profiles. So when should we run balanced partitioning and actually order our functions to improve compression or startup time? The LLVM prof data tool has an order command, which can read function traces from an index profile and can give you an order file. In this case, I have a.orderfile that is produced. And this order file can be passed to the linker to actually enforce the function order. The problem is that before build time, we don't have access to the contents of the functions because the instructions haven't been created yet. You haven't compiled anything yet. So we cannot compute the stable hashes we need to improve compressed size. Another option is to compute the function order in the linker. We can pass the index profile to the linker to actually get these function traces. And we also have access to the contents of our functions to compute the stable hashes we need to improve compressed size. And this function order optimization that we're doing doesn't really need to do any analysis of the machine code. It doesn't need to have any understanding of the machine code. And the transformation that it's doing is just reordering functions in the final binary, which we already do in the linker with a flag. So this is why I'd call this it's kind of a safe optimization to be done at link time. So just to quickly recap, we have balanced partitioning that is upstreamed, and we have temporal profiling that is upstreamed. But I have not yet upstreamed reordering these functions at link time, like I've shown. But I do plan to upstream this soon, so please keep an eye out for patches. And for the results, we ran tests on 3 iOS apps. I won't be going into details about these apps, but I will say that about 80% of the total app size is binaries, and about 20% of the functions in our profiles that we collected are hot. So 20% of the binary is hot. I also wanted to test against some open source app. So I built Firefox for iOS. I'm not an expert in building Firefox, so I only changed the build flags for the client binary, which makes up about 30% of the total app size, which is the largest binary in the Firefox app. So this graph shows the compressed size improvement without using profiles. So all functions were ordered to minimize the compressed size. In blue, we have the compressed size improvement over the whole IPA, which includes images and other assets that we don't control, or the compiler doesn't control. But in red, we show the improvement over only the binary code. So if we look at Firefox on the far right, we were able to improve the compressed size of the client binary by over 6% just by reordering functions. And in this next graph, we used profiles to order hot functions to improve startup while ordering cold functions to improve compressed size at the same time. You can see the compressed size improvement has reduced, but this is a trade-off you'll have to make if you want to improve startup time at the same time. In the next few slides, I'll try to show that we have reduced the number of page faults during startup. In this experiment, I built an app with the default function order and installed it to my local device. And then I connected it to my computer where I launched the app and then measured page fault data from the device. So in this graph, each dot is a page fault in the text segment. The x-axis is time, and the y-axis is the address of that page fault. So you can see as the app starts up, we get more page faults throughout the text segment. And then I repeated this experiment using an app with a optimal function order to improve startup time. And it's kind of hard to see the differences between these two graphs. So I ran these experiments multiple times, and I plotted them together here. The x-axis is still time, but the y-axis now shows the total number of page faults we have seen since the app has started up. So the higher the point is, the more page faults we've seen, and the longer startup is going to take. In red, we have the base binary, and in blue, we have the ordered binary. And you can clearly see that the ordered binary gives you fewer page faults throughout startup. So to quickly conclude, we've extended IRPGO with temporal profiling to collect function traces. We've also created the balanced partitioning algorithm to compute a function order, which can reduce page faults during startup by 40%. And it can also reduce the compressed size by almost 1 to 3%. So hopefully I've shown that PGO can be useful in the mobile space to improve startup time. But I'd like to explore more future work. For example, I think we can order data sections in the binary to improve performance by reducing page faults. And I also think we can improve compression by reordering the data segment. Also, similar to inlining we have in PGO, I think we can use profiles to guide outlining decisions to kind of trade off between performance and code size. And I'm excited to see what more we can do in this area, because I think we have a lot of work, a lot of room for improvements in the mobile space for PGO. So that's all I have. So thank you so much for listening.
Thank you. So questions? Okay.
Yeah. Thank you for the talk. Your optimization goal with temporal profiling is startup time. And you already demonstrated that these sometimes may come in conflict with order for compression size. I wonder if it also goes into conflict and somehow affects positively, negatively overall performance when you have also goal that bold has to reorder functions to maximize overall performance, not startup time.
You're asking if you can reorder functions to improve performance, not just startup time, or?
Well, I can use bold to reorder functions to improve performance, or I can enable temporal profiling that also reorders functions to improve startup time. Does it affect performance if I use temporal profiling in some way?
So I just missed that last part. I'm sorry.
Bold reorders functions.
Yeah.
The goal is to improve overall performance, not startup time.
Yeah.
Temporal profiling also reorders functions.
Oh, okay.
The
Yeah,
goal
I
is
see
to
what you're
improve
saying.
startup time, not overall performance.
Yeah,
If
yeah.
I use temporal profiling, does it affect performance with not only bold?
Yeah, yeah. Okay, I see what you're saying. So generally in the mobile space, most of our work we do is not CPU bound. It's actually, which is why we focus on startup time so much. So we don't, yeah. This is mostly focused on improving startup time. We haven't really explored how to improve performance, during steady state.
Please go ahead.
Thank you for the great presentation. I just want to know how can we instrument the data address so that you can do the reordering. For function is easy. We can add a new code, but for date, how can you?
Yeah, that's a great question. That's something we're actually kind of curious about too. It's pretty easy to instrument functions to tell like when they were executed. But I believe we can infer some information by looking at the data that the, like if you have a set of functions you know are important for startup time, we can look at the data that those functions reference and order those data early in the binary. We're also exploring if we can use some kind of memory profiling tool to instrument actual data so we can improve that. So yeah, we're kind of curious about it as well.
So about the memory profiling tool, so it relies on some machine capability instead of the pure software instrumentation.
Sorry, I didn't quite hear the end of that.
I'm just curious about how the memory profiling tools work to get the data address.
So I mean, we haven't done this work yet, so we don't exactly know yet.
Okay, thank you.
Okay. Yeah, please go ahead.
So where do the page faults exactly come from? Because you're talking about the binary is decompressing itself at startup.
No, so when a function executes, we get a page fault if it's being started up for the first time and the binary isn't in memory yet. It's already, I believe the app is decompressed at install time.
Oh, okay. So the compression has nothing to do with, that's just for the...
We want to make a small compressed size so we can install it quickly.
Yeah.
And we want to minimize page faults so we can launch quickly.
Okay. That makes sense. Because wouldn't you want to alter the register allocator if you do the compression the way you do? Because you want the same instruction with the same registers?
Yeah, that's actually a very good question. We have actually looked in if we can change the register allocator to make more consistent instructions in our functions, and the compressor would like that better. The problem is you have to consider, will that harm performance or code size even? So yeah, it's an interesting question.
Any more questions? All right, thank you, Alice, for your talk. And the next talk is at the 11:30.